Hello, everyone. My name is Dr. Rana EZZEDINE. I'm an assistant professor at the University of Florida. I'm very excited to be talking to you today about my research, the research that my colleagues and I have been doing, which is excavating for the origins of the chemical elements in the universe. The story of this talk and our research is quite an exciting one. It entails going back all the way to the origin, all the way to the Big Bang, to try to excavate for any hints that we can try to understand of how the chemical elements in the universe formed, how they evolved until the present day to form our world, to form our beings, to form everything that we see around us. Interestingly, we still don't know, or we still have a lot of open questions about the origins of the chemical elements. And so this is why I think this work is exciting and excites me every day to do it, because the basic things that make up our entire world, we still have open questions on. And I'm very happy to be showing you some of the work or some of the advances that we've done so far to understand these origins. Now, since this is a story of origins, it has to be, we have to go all the way back to the beginning of the origin, which is all the way back to the Big Bang. So it all started with the Big Bang. A few minutes after the Big Bang, the periodic table that we now know and love was only made from a few elements. It was empty. There was nothing in it to fill the periodic table, because the universe was only made from hydrogen, helium, and a few hints of lithium and beryllium. All the other elements, they were not formed via the Big Bang, but they were formed either inside or via the stars. And we're going to talk about this a little bit more later. Now, 100 million years after the Big Bang, the very first stars in the universe came to be. And inside these stars, the very first elements started to form that are heavier than lithium and beryllium, hydrogen, and helium. And these stars are very important, these very first stars, because they forged the very first elements in the universe that started life, that started everything. Now, interestingly, if we want to study the origins of the elements, you would think that the easiest way would be to go back and study the very first stars, because this is where the elements started. However, unfortunately, our current technologies, our current telescopes are not able to go back in time all the way to the first stars. This technology is still not available. It's not able to look all the way back to the early universe about 13 giga years ago. However, what we can observe nowadays, today, from our telescopes, from the technology that we have, is the second generation of stars, which is the stars that came after the first stars. So after the first stars have exploded, have died, and have emitted all of their chemical elements into what we call the interstellar medium, or the gas cloud from which the universe is full of, a second generation of stars started there, and we can observe those. However, the first stars, we really don't know anything about them, or we don't know much about them, because we haven't been able to observe them. We have, however, been able to study them theoretically by writing up or coding up cosmological simulations, starting all the way from the Big Bang in what we believe the universe was made of, which is mainly hydrogen, helium, and dark matter, which we know the universe is full of. But this is, of course, another talk, and not the concentration of this talk. And these cosmological simulations allow us to poke back into this region that we cannot observe with our current technology. And what I'm going to show you here is one of these cosmological simulations done by Brendan Griffin at MIT. It's going to show you two colors. So the red is what we call the first star's mini halo, or the mini halos which contain the very first stars in the universe. And in yellow, you are seeing the first galaxies. And as you can see that the first galaxies, and this is, by the way, a simulation similar to the formation of our Milky Way. So it was formed by the combination of lots of fragments of small first star mini halos that came together to form the very first galaxies, which is pretty cool and exciting for us to be able to kind of produce a galaxy similar to our Milky Way halo all the way back in the early universe. However, we are still unable to directly observe the evidence of these first stars. And right now, we just have to take whatever the simulations and the theory tells us. And what they tell us is that these stars, the very first stars in the universe, must have been very, very massive, because the universe was just made of big blobs of gas that would come together and form stars that are about 100 to about 1,000 times the mass of our sun. So very, very massive stars. Now, this is pretty exciting. However, unfortunately, that means that stars that are this massive, they cannot survive for a very long time. They would use their fuel up very, very fast. And so they would die pretty much after they are born. So within the uncertainties of the ages in astronomy, they would just live a few million years and then they would die. And so unfortunately, we know that these stars, the very first stars, cannot be found in the present day. Or if we want to observe them, we have to look back into the universe all the way to the Big Bang. Now, that's okay, because we have another way to try to understand the origin of the chemical elements by looking at what we call the second generation of stars. So the stars that came right after the first stars. But before we get to that, I want to tell you about the recipe for our understanding of the origin of the chemical elements. So we need basically two recipes or two main ingredients for us to understand the origins of the chemical elements. The first one is that we need to understand nuclear physics. We need to understand how the chemical elements form inside the stars or even during their deaths. So we know that there are two ways to make up the elements that we see in the periodic table. We divide them into light elements. Mainly these are ones that are less heavy than iron, because these are usually formed inside the stars, and so we'll talk about that in a minute. And then we have heavy elements in the periodic table, which are heavier than iron. So everything that's heavier than iron that takes up the lower space of the periodic table, these are usually formed by different techniques or different processes than the fusion that takes place inside the stars. Then the second recipe that we need to understand the origin of the chemical elements is astrophysics. So it's not enough for us to understand nuclear physics to know the origins of the chemical elements. We also need to know the conditions in which these elements are formed. And this is why we need to know astrophysics. We need to particularly know the chemical evolution. So how did the evolution of the elements take place all the way from the Big Bang until the present day, until our current being, basically, until the Earth was formed, until the Sun was formed, which is a young star. And we also need to understand stellar archaeology, which is at the heart of this talk. So this is what I'm going to be talking to you about for the rest of the talk. What is stellar archaeology and how do we use it mixed with chemical evolution and our current understanding of nuclear physics to understand the origin of the chemical elements. So let us start by nuclear astrophysics. We know that most of the elements up until iron are formed inside the stars, and this is by a process that we call nuclear fusion. So nuclear fusion, as you're seeing here in this animation, is basically bringing up multiple elements, bombarding them within each other, and then fusing them to form heavier and heavier elements. However, the thing about nuclear fusion inside stars is that it doesn't happen the same way in all types of stars. So massive stars, those that are about 8 or more times the mass of our sun, they have the capability to fuse elements at their cores up until iron, because they have enough energy. However, anything beyond iron is not capable or is not possible to be fused inside the stars. So we need a different process to produce these elements. Low mass stars or intermediate mass stars like our sun, so these are not able to fuse iron, or not able to fuse elements up until iron at their cores, and rather they would die by just poofing up their elements at the end of their lives into what we call a planetary nebula, whereas massive stars, they would reach iron core and then explode. But in any case, both of these stars, so whether it's a low mass star or a massive star, they are not able to produce elements that are heavier than iron. But we know that in our universe and in our periodic table, we have a lot of elements that are heavier than iron. So how are these produced? These are produced by a different method called neutron capture processes. And the neutron capture, from its name, it means that whatever element or whatever seed element is basically capturing neutrons and then making bigger atoms. And however, these atoms usually are unstable because not all the elements in the universe are stable. And so what they would do is they would beta decay onto atoms that have a lower atomic number until stability is reached. And we have two types of neutron capture processes. One that is called a slow neutron capture that we call the S process, and the other one is called a rapid neutron capture process, which requires a lot of neutrons very fast to take place. So we're going to talk a little bit about these, and this animation here shows you, for example, one of the neutron capture processes where you have a seed nucleus that is capturing lots of neutrons, and every time it's releasing some of its neutrinos and some of its elements to actually decay onto stability. The second recipe, as I said, for us to understand the origin of the chemical elements is to know or understand chemical evolution. And this is important because the buildup of the chemical elements, basically, the buildup of the elements just basically evolves over time. So what does this mean? It means that at the time of the Big Bang, as I said, the universe was made up, as you can see here at the lower left. The universe was made up of hydrogen, helium, mainly a little bit of lithium, beryllium, and boron. So this is at the time of the Big Bang, or a few seconds after the Big Bang. Everything heavier than that, as we said, is formed inside the first stars, or up until iron is formed in the very first stars. But these first stars, we've established that they were very massive, so they must have exploded by what we call type 2 supernovae, or with supernovae, and must have ejected their elements that were inside of them into the interstellar medium. And so the interstellar medium, or the gas, is now filled with elements that were originally inside the first stars. And after a while, this gas, including these elements, has time to cool down and then form other stars that we call now population 2 stars, or we call them second generation stars. But since this gas had time to cool, it has the possibility to create lower mass stars, so they don't have to be very big. And the cool thing about these low mass stars is that they have a chance to actually be present until today. So we can actually find them even in here in the Milky Way because they are low mass, and so they have time, they don't use up their fuel very fast, and they can live up to about 12 or 13 giga years, which is almost as much as the age of the universe. And so this is really cool because if we can find these stars which contain inside of them the very first fossils from the first stars, because they were enriched or they were formed from the gas that was previously enriched by a first star. If we can find these stars, we can then understand the origins of the chemical elements. Now, how do we find these stars? We apply, or how do we use them to understand the origin of the chemical elements? We apply stellar archaeology, which is at the heart of my research and what my colleagues and I do. So stellar archaeology is studying and finding these low mass stars that are very, very old, very, very ancient, that are still found in our galaxy and other galaxies today, and then using their chemical composition, so by studying what's inside of them in terms of elements, using these chemical compositions and abundances to trace back the star-forming gas cloud from which they were formed. And the reason for that is because this star-forming cloud must have been actually enriched by a first star. So as I said, the very first star, after it's died, it has poofed out all of its elements into a cloud, and this cloud, after a while, forms low mass stars, which are still found until the present day. So it's kind of like archaeology here on Earth. Archaeologists on Earth look up for fossils, the oldest fossils that they can find, to try to trace it back to the history of Earth and history of the culture or of civilization. We are doing the same thing by looking for the oldest fossils in our galaxy or in the universe, and these are these low mass stars that have survived all the way from the first stars until the present day. And so how do we find these oldest stars, and how do we study them? We have to study their chemical compositions by obtaining what we call spectra. So we do something called spectroscopic observations, but these stars are very, very rare, and most of the time they are very, very faint. So we cannot see them when we look up into the night sky. And so we need very specialized, very large telescopes, such as you see here on the left is the Magellan telescope, the Magellan twin telescopes that is found in the Atacama Desert at the Las Campanas Observatory in Chile. And on the right, you can see the Hubble Space Telescope. Sometimes we need even more resolution. We need to get out of the atmosphere of the Earth to get even better resolution of our stars. And so we can use the Hubble Space Telescope and other telescopes like it, which give us even higher resolution. And when we observe these stars, we obtain what we call a spectrum, what you see here at the bottom. And a spectrum basically contains all the elements, or they contain fingerprints of the elements that are found in the star that we are studying. So once we do that, once we obtain the spectrum of the star, we can then understand what kind of elements we study, what kind of elements it has. However, how do we identify that the star is old and it is indeed a second generation? Because there are tons of stars in our galaxy. How do we identify that this is really the fossil star that we are looking for, that has the imprints from the very first stars or from the Big Bang itself? In order for us to identify stars as being really old, we have to understand the chemical evolution, which is shown here in this cartoon on the left. So, as I said, chemical evolution entails that or the basic idea of chemical evolution is that stars, when they are born, they have inside of them, or they contain inside of them, the prints or the fingerprints of the cloud from which they were formed. So stars remember where they were born. This is the main idea of this talk, and also of why we can do the work that we do. So this means that if they were formed from a gas that has had time to get enriched multiple times along the age of the universe until the present day, such as our sun, which is a young star, then when we study it, we're not supposed, we can find hints in this star that tell us about this gas cloud. And the main idea is by studying what we call the elements or the metals in the star. So what are metals? Stars are made from 73% hydrogen and 25% helium. And the rest, which is a very, very tiny bit, is the rest of the elements we find in the periodic table. Now, we would expect the very early stars, or the very, very old stars, to have only a little bit of metals in their stars, to have a little bit of the other elements, because at that time the universe did not have time to recycle the elements multiple times in the universe, and so there was no time to actually create a large amount of these elements. Whereas younger stars like our sun, as I said, has had time to get enriched again and again by multiple events of star forming, supernova explosion, more elements out into the interstellar medium, another star forms, another supernova explosion, and so forth for a very, very long time, for about 12 giga-years. And so this means that the younger stars should have larger amounts of the other elements that we find in the periodic table. And I've talked about metals. Now, what does metals mean? For most people, metals mean, the metals that we find in our daily life, such as iron, such as, zinc, aluminum, etc. But in reality, astronomers have a different idea for metals. For astronomers, metals is literally anything that is heavier than hydrogen and helium. So this is what we call metals. And when I say that old stars have tiny, tiny bits of metals because it didn't have time to get enriched so much, it means that it had very, very tiny bits of all the elements that are heavier than hydrogen and helium, so including magnesium, calcium, iron, etc. Whereas younger stars has a lot of metals inside of them, so this means that they have a lot of iron, a lot of magnesium, etc. inside of them. And so the stars that are old, that did not have had time to form a lot of, or did not have had time to get enriched by lots of supernova explosions, etc., have very tiny bits of the heavy elements or the metals, and so we call them metal poor. So whenever we talk about a metal poor star, it means that it's an old star. Now, this is very important to remember. Okay, so how do we identify the elements? We now have a recipe that if we want to know the origin of the elements, we have to find a star that is a fossil, which means it's very, very old, and we have to study its chemical compositions, and because the chemical composition tells us about how old it is. So if it has a little bit of elements, it means it's old. But how do we do this? How does this process work? As I said, in order for us to study these stars, or any star, or the composition of a star, we have to obtain what we call a spectrum. And we do that by going to the big telescopes and obtaining the data. And why is a spectrum important to understand the composition or study the composition? Because spectra have fingerprints onto them that allow us to know what kind of elements exist inside the star. So you can see an example here of our sun's spectrum. It's a beautiful rainbow that we sometimes see when it rains. However, on this rainbow, you can see some black prints of missing light. And it seems as if something was there inside the sun that absorbed the light. And instead of seeing the light in some of these areas, we are seeing a dark patch. So what does this dark patch mean? It means, just like when we are looking here, for example, in a prism, with a prism, which allows us to see the rainbow, if you are looking directly at the prism, so if you have a lamplight and you have the prism in front of you and you're looking at it from the other side, you can see all of the rainbow, so you see very nicely. However, if you remove the light and you put a gas in front of the prism and you look at it, you can see what we call emission lines. So emission are lines that come out from the gas, indicating that inside of the gas, there are elements, there are chemical elements that make up the gas, such as neon or other stuff. Now, if we do the same thing, if we bring a lamp, which in this case represents our star, and we put a gas instead of the lamp, which in this case represents the elements found in the star, or the gas inside the star, what we see is we call them absorption lines, which means the missing lines in our spectrum indicate the elements that have absorbed light that are found inside the stars. And this is actually very interesting work that has been done, that was done for the very first time and was identified by Annie Jumpcannon, who was at Harvard University at the time. She identified that stars have unique fingerprints that tell us so much about them and tell us about their properties, including their chemical compositions, just by looking at these unique spectral lines or absorption lines that are found at specific places inside the spectrum of a star. And you can see here an example here at the bottom where each of these dark patches or missing light patches or absorption lines indicate or correspond to a specific element. And nowadays, when we look at a line or an absorption line that lies at a specific wavelengths from the light that we're studying, we know that this corresponds, for example, to iron, to sodium, to hydrogen, etc. And this is all because of very, very pioneering work that was done by Annie Jumpcannon and her colleagues at the time. So it's very exciting. And so that's pretty neat. We look at the fingerprints of the star that we obtain from a spectrum, from a telescope, and it tells us what kind of elements are there. Now, how do we identify that a star is old or not from this spectrum? As I said, the oldest stars, the oldest fossils that help us identify the origins of the elements should have very little metals inside of them, or as I call them, metal poor. And so this should also be imprinted on their spectrum. And I can show you here an example. What you're seeing here in this diagram are 4 spectra of 4 different stars. From the top to the bottom, the very high spectrum has a lot of absorption features. So you see a lot of things going on in there, which indicates that there's a lot of elements in there, or that the composition of this star has a lot of elements and a lot of metals inside of it, including iron. And indeed, this is the case because this is a spectrum of a very metal-rich star, which is our sun. So it has a lot of metal. It's a young star. But as we go downward, we are looking back in time, which means we are looking at older and older stars. And so looking at the same place in the spectra of these stars, we are actually finding smaller and smaller absorption lines, which indicate that the star is older because it has much less metals inside of it. And so when we want to look for the oldest stars, we collect a lot of data, we collect a lot of spectra of a lot of stars, and those that have the very tiniest absorption lines tell us that these are old stars or metal poor stars. And the more metal poor they are, the better, because that means they're older. And so they are really pristine fossils that can tell us about the origin. So when we identify these stars, we look at all of their chemical elements and try to use that to understand the different origins of the chemical elements. And this is here, this is actually demonstrated here. So basically, the older the star, the less heavy elements it has in its atmosphere, just because as time goes on, so as you see here on the axis, on the horizontal axis, you have time and evolution. As time evolves throughout the universe, the heavy elements or the stars explode and they enrich the gas cloud with more heavy elements, so forth and so on. And so this is why the very, very old stars have very little of these heavy elements. And these are the stars that my colleagues and I are trying to find and study in order to understand the origins of the chemical elements. Now, you must be wondering now, what are the stories that we have learned from our studies of the origins of the chemical elements? Obviously, the periodic table is a very, very large and very exciting table because it has so many elements, and I can tell you lots of stories about what we've learned of how different elements have formed. However, I'm going to concentrate on a very specific story that recently happened, and it's an exciting story because it allowed us to understand how gold and uranium and similar elements got to form in the universe. And this was a question that was still open and that we didn't know the answer to until 2017. So as recent as that, we did not know how gold and uranium formed in the universe. But we finally have a hint of an answer, which is very exciting. And so this is why I want to concentrate on these elements and talk to you specifically about how elements are formed via the R process. So remember, we talked about the R process. It means the rapid neutron capture process. So again, this is our beautiful periodic table showing. I mentioned that inside the stars, elements only up until iron and with supernova explosions, some elements beyond iron, such as cobalt, nickel, copper, zinc, are able to form. However, anything heavier than that, so in the lower part of the periodic table, we need a different process to form these elements, and so they are formed by what we call neutron capture. So as I said, you have a seed nucleus, and this seed nucleus starts capturing lots of neutrons to form heavier elements. Now, we said we have two types of neutron capture. One is called the S process, and this is usually this is a slow process, so the neutrons don't have to have a very, very rapid flux, but rather a slow one. And we know that the S process takes place in evolved stars, such as stars that we call asymptotic giant branch stars. So these are stars that have evolved very much in their lives that allow this process to take place. However, there are other elements, particularly those such as thorium and uranium, which you can see at the bottom of the periodic table. These are elements in addition to the S. So the same elements as the S that are formed with the S process are also formed with the R process. However, they are formed with a much higher efficiency because the neutron flux is larger. And for the very, very long time, people did not know what causes or what are the sites of the R process. What can cause this very rapid flux of neutrons to form such huge amount of heavy elements in the universe? And this was an open question, and people have theorized different ways that the rapid neutron capture process can take place. One of them was the idea that we need a lot of neutrons, or we need a huge flux of neutrons. And we do have objects in our universe called neutron stars, which are the remnants of some of the massive stars. When they explode with a supernova explosion, they would have a remnant called a neutron star, which is a very, very dense, heavy object. Now, if we happen to have two neutron stars that are the remnants of two massive stars that were previously rotating around each other, so they were binary system, these neutron stars can then still rotate around each other and eventually merge together. And in this merging, they would form a very, very huge flux of neutrons because they obviously have a ton of it, inside of them. And this event, so the merger of two neutron stars, was believed or was theorized to be the main site or the dominant side of what we call the R process. And I showed you here a small animation of how the R process takes place, which is a very, very fast event. So what you see here on the x-axis is the number of neutrons, and then you have on the y-axis you have the number of protons, so Z. And so what happened is that at the time the neutron star merger started, you see a huge flux or a huge bounce of elements starting to form heavier and heavier elements up along what we call the chart of nuclides. And so heavier elements are forming, they're beta decaying, forming, beta decaying, etc., until we reach all of the elements up until uranium and thorium in our periodic table. And within, very, very few years, so within 32 years, which of course in astronomy is equivalent to milliseconds, is nothing, it forms all of these very, very heavy elements that we were looking for. However, the problem was, before 2017, people did not believe or have never seen signatures of two neutron stars actually merging together. We have never been able to observe this phenomena. But before we talk about this, in 2016, a breakthrough or a groundbreaking discovery led the way for us to start to understand the R process. In 2016, LIGO, or the experiment for gravitational waves, that is a major breakthrough, was able to detect for the very first time a gravitational wave signal that came from merging of two black holes. So these black holes, one was 36 and the other 29 times the mass of our sun, merged together, in 2015. However, they were published in 2016, the results. So when LIGO announced that they detected for the very first time gravitational waves, which was for a very long time suggested by Einstein to be detected, however, people were not able to do them yet because we didn't have the technology. This was so important because it meant that two very heavy objects, such as black holes or neutron stars, can actually be found in the universe and detected. And so this got people very excited to try to find, instead of two black holes merging, rather two neutron stars, which are as heavy, or even well, they are less heavy than black holes, but they are as heavy and dense objects. And so maybe we can actually detect gravitational waves that indicate neutron stars merging, and then we can understand if our process elements are formed during that event. And indeed, in 2017, the universe gave us a beautiful gift, one of the most amazing gifts, in my opinion, which is on 17th of August 2017, LIGO and Virgo, both gravitational wave experiments in the US and in Europe, were able to detect for the very first time two neutron stars merging together and forming such an energetic event that causes ripples in the time-space continuum, which creates a gravitational wave. And when they detected this gravitational wave, every single telescope in the entire world pointed their telescopes toward this location where these two neutron stars merged. And from the Earth, different telescopes at different wavelengths were looking at this event, and they identified something very interesting, or a phenomena rare and interesting, called a kilonova. they were able to observe signals of a kilonova that took place seconds or minutes after the gravitational wave signal was detected from the, and from that they identified that these two neutron stars, when they merged, they emitted a radiation or a flux that is called the kilonova, which is powered by the radioactive decay of tons of our process elements. And so for the very first time, we were able to confirm that indeed the formation of the heavy elements in the universe, such as gold, such as platinum, such as uranium and thorium, happens in the merger of a neutron star merger, and we were only able to confirm it in 2017. So now we have a lot of exciting work to do to try to better understand this by hopefully observing more of these events and trying to understand how different they are and how does this affect the production of these elements. Now, this was all very exciting, of course, the detection of gravitational waves, the detection of neutron star mergers and the kilonova and what that meant for the R process. However, one thing was missing is that in this event, even though we were able to observe a kilonova, which is a signature of our process taking place, we were not able to measure the elements themselves because this is a very fast ejecta. So this is a very energetic event. And so we were not able to see the R process themselves. We were not able to see gold in this event or other elements. And so all of this press that at the time that came out from every single major press source or press release that told us that you know, we were able to see gold, that gold was detected. There was a lot of talk about gold, of course, because we all know how important it is for humans, gold. Unfortunately, we did not see the gold during the event itself, and we are not able to understand the formation of gold itself from studying the event itself, but rather taking us back to the beginning of my talk. In order for us to understand the R process or the formation of any element, we have to go back to objects that are very pristine, that have not yet been polluted by lots of these events. And so this is why we have to observe the R process again, not in the event itself. While the event gave us a lot of information, to understand it better, we have to study the spectra of the oldest stars for signatures of the R process. And this is one of my major research areas, is to look for stars that show in their spectra fingerprints of the R process. And we usually do that by looking for several elements of the heavy elements. One of them, one of the main elements, or one of the main precursors of the R process is the element europium, which you can see here. It has an atomic number of 63. And you can see that we indeed observe it in a number of stars, and this number of stars is increasing thanks to the work that I'm doing with my colleagues. So what you are seeing here are the spectra of two stars, one in red and one in blue. The star that shows a spectrum in red is called HE 15230901. This is just its coordinates. But this star is very important because it was one of the first old stars that was observed where we clearly see a large signatures of the R process. So you see all these elements such as lanthanum, samarium, cerium, yttrium, europium also. So it showed us that the R process had happened at some time before this star was formed in the gas cloud from which this star was formed. Whereas the blue spectrum shows a comparison with an old star as well, called HD 122563, that does not show enhancement or does not show large signatures of the R process, which means that whatever gas cloud it was formed was not enriched by a neutron star merger event, and so does not have the signature of the R process on it. So it means that even though we have two old stars, probably with the same amount of metal content, one of them must have been enhanced or must have been enriched by an R process event before it was formed, whereas the other not. So our job is now to try to find and identify more of these stars that show the R process enhancement and or the R process signature, and then trace it back to the different events or the different properties of the neutron star mergers which actually form these elements. And this is a work in progress that is still has lots of exciting avenues to try to look for and also to study. So in summary, or finally, as I told you, my research and what I told you about this small journey that I hope you had enjoyed taking with me is called stellar archaeology. My research is stellar archaeology, and I use stellar archaeology to understand the chemical evolution of the elements and also the chemical origins of the elements. And I gave you an example of a very recent story of how very recently we were able to identify the origin of gold and uranium and other heavy elements that are formed via the S process. And so as a stellar archaeologist myself, so basically I'm like the Indiana Jones of the galaxy, I am trying to search for the oldest fossils in our Milky Way, but also maybe in other galaxies. The Milky Way is our home. This is why it's easier to find these fossils. Our technology does not allow us yet to look for old stars in other galaxies, but maybe one day we'll be able to do that. So just like archaeologists here on Earth are searching for the oldest fossils in order to understand its history, me and my colleagues are also searching for and studying the oldest stars in the Milky Way, hopefully to find exciting elements in them, such as those of the heavy elements formed by the R process. And when we do that, when we identify these stars, we go toward the biggest telescope in the world, such as the Grand Telescopic Canarias or the GTC in the Canary Island, or the Magellan twin telescopes that I've told you about before, in Chile, in the Atacama Desert, or the forthcoming, the very exciting telescope, the biggest telescope. It's going to be a 28-meter telescope that's coming also in Chile, called the Giant Magellan Telescope, that allow us to study the fingerprints of the stars and hopefully continue to better understand the formation of the chemical elements and how they've evolved through time to form everything else, to form life, to form us. And this will also help us also understand whether we're able to find life elsewhere and how that life could have evolved in exoplanets. Now, I'm sure you will hear other talks throughout this conference or this festival about exoplanets, which is all very exciting. But for that, we need to understand, in order to understand life, we need to understand the chemical elements. So thank you very much for listening to this talk. I really hope that you have enjoyed it. Please feel free to ask me questions during the live chat that is coming up on the 11th of August, and keep looking up. And as I said, I'm an observer that goes to big telescopes to study and look for the oldest stars. But as you can see, this is me in the Las Campanas Observatory trying to take a photo with the Milky Way right in front of the telescope. But we are having major problems as astronomers fighting light pollution. So please join us in this cause to fight light pollution whenever you can, because in order to continue to discover the secrets of the cosmos as astronomers and as humans, we really need to keep our skies polluted free. We need it to be dark. We cannot do it when we have an increasing amount of light pollution. So please take that into account the next time you look up. And thank you very much for listening.